students, in continuation to my videos, today I will discuss electric field lines. You remember magnetic field lines in class 10th? In a bar magnet, how the magnetic field lines move from north to south outside the bar magnet and south to north inside the bar magnet. Same is with the electric field lines, and these are also known as electric lines of force. You know, the electrostatic force is due to these lines only, and they were first, that introduced by Michael Faraday. Now, what is the how you define electric field line? Actually, an electric line of force. An electric line of force is the curve. It is the curve along which a small positive charge would tend to move when free to do so in an electric field, and the tangent at which at any point gives the direction of electric field intensity. So this is how we define electric lines of force. Now if you see electric lines of force, that is, that the tangential to at any point will be the direction. Say this is a line and there are points A, B and say C. So electric field will be like this, EA tangential to the point EB and then is EC. You remember you have gone through this streamline motion in class 11th, and you know that Bernoulli's theorem. Before Bernoulli's theorem there were streamlines, and in 10th it was electric or magnetic field lines. Now it is electric lines of force. Now electric field lines have some properties. What are the properties? The properties are related with the lines of force. So properties, electric line of force, electric field lines. What are the properties? One by one we can discuss. One is that lines of force are continuous. They are continuous. They doesn't have sudden breaks. So no sudden breaks. There can be a question on this also. No sudden breaks. They are continuous. Then is that they start at positive charge and end at negative charge Okay, then tangent to line of force, already I have mentioned it. Tangent to line of force is direction of what? Electric field intensity, E. Then there is a very important property, you remember it? No two lines of force can cross each other. Lines of force can cross each other. You remember, no two streamlines can cross each other. No two magnetic field lines can cross each other, because at a point where they cross each other, there will be two directions, and that's not possible at a point as they all are vector quantity. Then there is another property that they are normal to the surface of conductor. They are normal to the surface of conductor. So this is also a property. And another important is that they doesn't pass through the conductor. So doesn't pass through the conductor. through the conductor. So this is how we say, that means if this is a conductor and any electric field lines is coming like this, and if it is going like this, then this is the wrong one. So this can't, because they can't pass through the conductor if it is a conductor. So these are the basic properties of lines of force. Now we can draw the lines of force. You know that they are continuous. They start from positive and end at the negative charge. They are tangent to the lines of force. No two lines can cross each other. They are normal to the surface of conductor. They doesn't pass through the conductor. Now I will talk about how we draw the lines for the charge. Now if we see a positive charge, now for a positive charge, if I have a positive charge plus, and then another is the negative charge. Okay, so positive charge, negative charge. For positive charge, the lines of force are, you know that they are away from the conductor, so they will be like this. These are the charges. You can draw like this, and these are the lines of force. For a negative charge, the lines of force are like same, but they are inward. So if you draw them, they will be like this. The direction is inward. So these are the direction for positive and negative charge. One is plus Q and one is minus Q. Okay, so sometime it will be in the question that draw the lines for the charge Q greater than 0, Q less than 0. Q greater than 0 means that is a positive charge, and Q less than 0, it means it's a negative charge. So positive and negative charge, you can draw the lines for positive and negative charge. Now if these charges are given in the pairs, now how pairs, I will explain you how they are given in the pairs. Say in the paper it comes, question, draw lines of force for Q1, Q2 greater than 0. Now Q1, Q2 greater than 0 is simple, that both are what? Like charges. One is say this plus, and the another is what? Q2, this one. So this is Q1, this is Q2. Now lines of charge, very simple how you are going to draw it, because we know that both charges will repel each other. So the direction will be like this. Direction will be like this. Okay, so because they are moving away. Now in the same way for this will show the repulsion, the lines of force will move out. So, and in this region, you know that the repulsion will take place somewhere, the electric field will be 0. So this is the way we can draw the lines of force for Q1, Q2 greater than 0. Now if you want to draw it for Q1, Q2, and somewhere there will be a null point, say here, that means where the electric field will be 0. So Q1 and Q2 charges repel each other. Now the next one, if I draw it for the charge Q1, Q2, say the question comes the same way, draw line of force, electric field lines of force for Q1, Q2 less than 0. Now that means unlike charge. Where here we say that these are the unlike charges. One is positive and the other is negative. So one is say positive and the other is what? Negative. So these are the two charges. Now what happens? They will attract. The lines will move from here to here. The lines will move from here to here. So this is the way the lines, they move out. they start from positive charge, they end at negative charge. And this is the line moving out, so this will enter from here. In this way, the lines, they enter and they move out from this charge. So this is positive charge, this is negative charge. You can draw the line of force for unlike charges. So in this way, we see that there will be somewhere null point outside here or here. You can find out depending on the magnitude of the charges. So this is how we draw the lines of force for Q1, Q2, what less than 0. Now there is another case that uniform and non-uniform electric field. That also I will discuss. Uniform and non-uniform electric field. So generally we have the cases of uniform electric field. Uniform electric field is a concept where the lines are like this, equidistant parallel lines. They represent what? Uniform electric field. Uniform electric field. Say there are charges at A, B, C, and all the charges are of magnitude Q, Q. So in all the case, the force will be same. And we know that the force is what? QE. So this is a uniform electric field. These are the equidistant parallel lines. So we will have these cases of uniform. Non-uniform electric field, we know that the non-uniform electric field are like this. Like this. So if the lines are going like this from any surface from one end to the other end, say this is the point A and this is the point B, certainly the electric field at A is greater than B and the force at A will be greater than B. So it's a non-uniform, non-uniform electric field. So this is how we see uniform and non-uniform. Generally we have the case of uniform electric field in our slabs. So these are the things which are related with electric field lines. And now you know that we can discuss about the superposition in electric field intensity. Very simple. Superposition already I have explained you in electrostatic force. Superposition in electric field intensity. Now say there are two charges. If I ask you, one is positive and the other one is positive, so say plus Q. So we know that somewhere at the center the electric field will be 0. Why? Because the direction will make it 0. From here it will be in this direction, from here it will be in this direction. Net electric field is what? 0 at the center. Always the electric field from a positive charge is away. Okay, and from a negative charge to a negative charge at a point is towards. This is the point, electric field will be away. This is the point, electric field will be towards. That means if one charge is positive and the other charge is what? Negative, and both are of same magnitude, one is of Q, other is of Q, certainly the electric field at the center, say this is positive charge, so the direction will be here, and negative also. So this electric field is what? Doubled. So it will be double of both. So this will be the direction. So this is how we define that we calculate the electric field due to the superposition, and this is also that known as neutral point. Okay, so superposition we can do 1-2 questions based on this. I will just explain you. Say two charges are there, 16 microcoulomb and 4 microcoulomb. Okay, separated by say 4 centimeter, and the question is find the position of neutral point. Or neutral point means what? Neutral point is that where electric field is what? 0. So there are two charges. One is of say 16 microcoulomb and another of 4 microcoulomb, and both are positive. And certainly we know that somewhere the electric field will be 0. And where it will be 0, you know that it is a greater charge, so it will, and it is a less charge, so it will be near to this point. So here we can say this is the point. Now this distance is 4 centimeters. Say this is x and this is 4 minus what x. Total distance is what? 4 centimeter. So what we can say at this point, electric field E1 will be equal to E2 because net E is what? 0. Like we have done it in electrostatic force. So KQ by R square, KQ1 R1 square, KQ2 by R2 square. This is the electric field. You remember the electric field? What is that? KQ by R square. So we can write it. KK will be cancelled out. This 16 by R1 is X microcoulomb. Okay, and this is 4 microcoulomb by what? 4 minus X square. So cancel out 4 just 16. 4 by X square. It is 1 upon 4 minus X whole square. And finally square will be out. So 2 by X we can be written as 1 upon 4 minus. Solve it out. It becomes 2 4 minus X equal to X. So it is 8 equal to 3x. X equal to what? 8 by 3 centimeter. So the electric fields are 0. 16, so 8 by 3 centimeter from which charge? From plus 16 microcoulomb. So this way we can follow the superposition in electric field intensity. Now there's a word electric flux. Okay, after electric field we have a word electric flux. Now how we define electric flux? You know that magnetic flux, electric flux. Electric flux is basically, it's a scalar quantity. If you see the lines are passing through a cross-sectional area. So how you define? So the number of electric field lines passing through a closed surface is known as electric flux. That's known as electric flux. And electric flux is denoted by phi. So phi is an electric flux. The another definition is that it is the dot product of electric field intensity and area vector. So we can even say phi is E dot A, phi is EA cos theta. Remember, dot product, and SI unit is Newton per coulomb for E and meter square. So this is electric flux. So you have two definitions. One is the dot product and one is the number of electric field lines passing through a surface. And some of you may be thinking about that, what is an area vector? I will tell you what is an area vector. Say for example, this is a charged surface. Now this is a charged surface. You know that every surface has a normal to it, and that normal to the surface is known as area vector. Say this has an area, so the area vector will be normal to it and outward. Okay. Now right now this is a positive surface. Where is the direction of electric field? Outward, because positive means away. So flux will be what? Maximum. Why? Because EA, what is the angle between them? Is theta equal to 0 degree. EA cos 0 is mean what? 1. Now if I say that this is the charged surface, okay, where is the area vector? Normal to this. But if the electric field lines are passing like this on any surface, say it's not a charged surface, it's a simple surface, we can say, okay, and electric field lines are coming. So we can say that EA cos what? EA cos what? 90. So it is 0. Another one is that there is another surface. there we can say that the area vector is out, but the electric field is down. So tell me what will be it? EA cos 180. So we can say that it is minus EA. That is, it is minimum. So flux is nothing. It is the product of E dot A. A is here is area vector. Area vector is the orientation of the area of the surface area. So we can see that how we find out the area vector in this case. So this is electric flux. We'll carry on later on in this topic.